हाँ नहीं वो दिखेगा गो
Started. Okay, good morning, students. Okay, fine. We have started the solution, and the topics which we cleared. What the first one was the saturated and unsaturated solution. Then we discussed the concentrations of the solution, and then after we discussed the various type of the solutions. The first one was that the gas in the liquid. Second was the liquid in the liquid, and the third one today I'm going to start that solid in the liquid. So we'll discuss a few things about the solid in the liquid, and I think one of the topic is left in the previous lecture that was solution of the liquid in the liquid. Okay, so we'll discuss the first thing. In the liquid and liquid solution, we have derived a formula to calculate the P total, and we discuss the mole fractions in the vapor form. So let's see that what happens after that. Is it clear? Done. So first of all, I want to just explain about the when a liquid is dissolved in the liquid, then what could be the variation in the vapor pressure, and we'll describe with the help of a graph. So let's discuss the Raoult's law graph. First of all, I need to discuss the Raoult's law graph. See. So this is the Raoult's law graph. Here we take the mole fraction, and here vapor pressure, and that side also vapor pressure. Actually, it's a combination of the two graphs. The first one at this point will take that x1, that is the mole fraction of the first liquid, which will be taken as 1, and x2 will be equal to 0. Because initially the first solution, only one solution is present, and second solution is absent. In the second part, we'll see that x1 will be equal to 0 and x2 will be equal to 1. In this part, we'll see that the second solution will be maximum. But when we mix them together, what happens that then mole fraction will be varied. Is it when that will not be equal to 1 for the individual. So x1 plus x2 will be equal to 1, but for the individual, for x1 or x2, it will be different. Is it fine? So let's see that if it is x1, then I told you that the mole fraction of this one, this was taken in x1, and if we talk about the partial pressure of it1, so this will be P1 is directly proportional to the x1, and for the second one it was the P2 is directly proportional to the x2. The same thing we have seen in the when a gas was dissolved in the liquid. Is it fine? But that time the Henry's law was associated with, but this time this is the Raoult's law. So here we have seen earlier like P1 is equal to P1 naught x1 and P2 is equal to P2 naught x2. Is it fine? So these are the two formulas for the individual partial pressures of the individual liquids. Now we have to show it on the graph. So if it x is equal to 1, then the partial pressure, so vapor pressure in the purest form will be taken as a P1, and vapor pressure of the second liquid will be taken as a P2 naught. Okay, so here it is. You will see that if I take this as a P1 naught, and this will be taken as a P2 naught. Why I have taken P1 naught? What is the reason behind it? Because x1 is equal to 1, so therefore the mole vapor pressure in the pure form will be P1 naught. If mole fraction is x2, then vapor pressure in the purest form will be taken as a P2. Now we just plot a graph here, and it will go this side, okay, and this will go that side. Is it clear, students? So this graph from x1 to the P2, then it will be taken as P2 is equal to P2 naught x2, and this graph will be taken as a P1 is equal to P1 naught x1. Is it clear? Now, if you combine these 2 points, suppose if we combine, then we get the P total. The P total is equal to what answer? P1 plus P2. So this is the combination of the two liquids. Is it fine? And both are volatile in the nature. So this was the Raoult's law graph. Okay. Now we'll talk about that mole fraction in the vapor form. What happens? When the liquids, both the liquids, when combined together, and we form a solution, and both are volatile in the nature, and after that they will convert it into the vapor form. Then what will be the mole fraction in the vapor form? So the mole fraction in the liquid form will be taken as x1 and x2. Is it fine? Now in the vapor form we'll take the second thing, that will be y1 and second will be the y. Is it clear? So x1 and x2 when they are in the native form, that is in the liquid form, and y1 and y2, these are the mole fraction when they are evaporated and they will be moved into the vapor form. Is it clear? So what will be the formula for that? x1 and x2 we can find out by these formulas. P1 is equal to P1 naught x1 and P2 is equal to P2 naught x2. But what about the y1 and y2? In case of the y1 and y2, the another formula will be used for this, in which we will use the p total. So what is that answer? Y1 is equal to p1 upon p total. Okay, and y2 is equal to p2 divided by p total. Is it fine? So y1 is a mole fraction in the vapor form. P1 is the partial pressure in the solution of the liquid number 1, and P total, this is the total vapor pressure of the liquid 1 and the 2 in the solution. Now Y2 is equal to the same thing, is the vapor pressure of the liquid 2 in the solution, and this one P total we have already discussed. So these are the two formulas by which we can calculate the vapor pressure in the vapor form. Sorry, partial pressure in the vapor form. Did you understand? Any question till here? I need to start the second topic now. Already I have given the description in the earlier class. So let me see that how many students are giving the response. So see that. Is it there? Any questions, students? Satya, she is having no doubt. Any other student who is watching? Okay, fine, good. Nikhil, then Shalini. Okay, P1 is X1. No. P1, beta, Shalini, just listen. P1 is equal to P1 not X1. This already I have explained in the class. P1 not is what? Suppose, please, can you provide me these two bottles if it is possible? But I have two liquids. Is it fine? This is liquid number A and this is liquid number 2. Fine. Now, if you talk about, this is a question which was asked by the Shalini. This is for the Shalini. Fine, just listen. In the liquid number 1, this is the purest form. And if I close the lid, then what happened after some time? You see that vapors are produced in it, and these vapors will apply the pressure on the walls of this bottle. Is it fine? So the P1, the vapor pressure of this solution will be P1 naught because it is in the purest form. Now come to the second liquid. This is the liquid number 2. Is it fine? So the vapor, it will also produce the vapors, and these vapors will apply the pressure on the walls. So its vapor pressure in the purest form will be taken as a P2 naught. Is it fine? That is what P1 naught for this one and P2 naught for this one. When we combine these two, when we mix them together, then both the solution are mixed together. Is it fine? And both the molecules are present in this. So now the total vapor pressure will be taken as a P total, and P total will be P1 and P2. Now, what will be the value of P1 and P2? This is the question. So P1 will be, you know that P1, vapor pressure of the first liquid, partial pressure of the first liquid will be directly proportional to the mole fraction. Now come to this point. The quantity of X1, the quantity of the liquid number 1 will decide the vapor pressure of the liquid one in the solution. Now quantity of the X2 will be responsible for the deciding the vapor pressure of the second liquid. So understood this thing? Quantity of the first liquid will be responsible for the deciding the partial pressure of the liquid 1, and quantity of the liquid 2 will be deciding the partial pressure of the liquid 2 in the solution form. Is it fine? So we need to calculate this thing. That P1 is directly proportional to X1 and P2 is directly proportional to X2. Now, if you remove this proportionality sign, then this is the P1 naught. P1 naught is what? The partial vapor pressure in the purest form of the liquid number 1, and this one P2 naught is the partial pressure in the purest form of the liquid 2. This is the formula. So here you have written like P1 is equal to XP1. It's not XP1. It was the Dalton's law which we have discussed last year, and this formula is applicable for only one of the component which is volatile in the nature. But here this is the liquid and liquid solution. These are the two formulas. That P1 is equal to P1 naught and X1, and P2 is equal to P2 naught and X2. Is it fine? So here you have taken P1. It's not P1. It is P1 naught, and this one is P2 naught. I hope it is clear. Shaheen. Okay, fine. Shalini agreed to this point. Now, second one is the Kavita Agarwal. She was asking me that Y1 and Y2 are the mole fractions in the vapor form. See, when they are liquid in the form, so their mole fraction was taken as x1 and x2. But when they get evaporated and they form the vapors, then these vapors will have the y1 and y2 as a mole fraction. I hope you clear with this. Okay, fine. So all are clear with the topics, isn't it? So let's discuss on the second topic. So this was the round snow and everything. I'm not removing this graph because we will use this graph later. So we have two things with us. The one is when a gas is dissolved in the liquid, then we have got the formula that was P1 is equal to KHX1. Is it fine? And the second one was there that P is equal to P naught whatever, like Px and Px naught is equal to x. Understood? These are, so this is the Henry's constant, Henry's law, and second one is the Raoult's. So what are the difference between the Henry's law and the Raoult's? So this is the next question. Okay. So I already explained earlier, like if you take a liquid and in that if you dissolve a gas, you try to dissolve a gas by just applying the pressure. Is it fine? So gas will be in the relative form that gas. So initially only one pressure will be exerted by the solution, that will be by the gas. So we are taking this as Henry's law. Is it fine? But in case of the liquid solution, two volatile liquids are participating in making the solutions. Is it fine? So both will form the vapors, and these vapors will apply the partial pressure. Is it fine? On the walls of the container in which they are present. That's why we are taking P1 and P2. So we can say that Raoult's law is a special case of the Henry's law. Henry's law can be used for the solution which are made by the gas in the liquid, and Raoult's law will be used when liquid is dissolved in the liquid and vapor pressure of these liquids. So this is the special case of the Henry's law. I hope you all understood this thing. So this was a small topic. Now come to the third type of the solution. What happens when a solid is dissolved in the liquid? So now next question is this. So anyone knows about that? What happens when the solid is dissolved in the liquid? What do you observe? I think any answer I expect from the students, if they can give me. What do you observe when a solid is dissolved in the liquid? No one is answering. I expect at least one answer from the students. Anyone? What do you understand? What do you think that what happens when a solid is dissolved? The solid is soluble. Obviously, the solid should be soluble in the water, or we can say in the liquid. Volume remains same. Okay. Any other? That's good. No problem at all. This nice answer. It's a clear solution. Okay, fine. It gets dissolved in it. Okay. Okay, fine. So I have got the three answers from the students. The first one is volume remains same. I agree with this point. I'll come to know. I'll let you know about it. I'll definitely let you know why the volume remains same. Now come to the second one. That's a clear solution. It gets dissolved in it. Solid particles take empty spaces. Very good. This is the good answer given by the research which. Okay, fine, good. So let's see. Okay, enough. I mean, it is a homogeneous solution, obviously. Great. Okay, fine. Now come to the board. Listen. Suppose if we take one container, and in this you will see that these are the solvent molecules, and solvent is a liquid in form. You can see that all molecules are of same kind. Okay, this is a pure solvent. Is it fine? Now you see that vapors are formed by this solvent will be similar type. Is there any change in the vapor? I mean, is there any difference in the vapors molecule and the liquid molecule? I think no. Solvent molecules and the vapor molecules of the same solution will be same. So it is a pure solvent, we can say. Now in the second case, what happens? If we take the same container and we take the solvent and we try to dissolve the solute molecules, and then I am taking the other color of the chalk which shows the presence of the solvent in intermolecular space is present in between them. The first answer was given by one student. Okay, he told that it was Prisha. She told that the volume remains same. You can see that initially the volume was like this, and after dissolution of the solute molecules in that, the volume remains same. So the answer was here. Answer is here. Here you can see that the intermolecular space present between the particles, among the particles in these intermolecular spaces, the solute molecules will be dissolved. Is it fine? Now the next thing comes. Initially, you can see that 1, 2, 3, 4. 4 molecules are present on the surface. Is it fine? Here you can see that in the pure form, 1, 2, 3, 4, 5, 6 molecules. Suppose we are taking, there are infinite numbers of the molecules, but here, for example, we take that in the pure solvent, you can see that how many molecules are there? 1, 2, 3, 4, 5, 6 molecules are there, right? But after dissolution of the solute in that, how many number of particles are on the surface? 1, 2, 3, 4. Is it fine? So here you can see that 1, 2, 3, 4, 5, 6, 6 molecules will get evaporated. But in this case, how many molecules will get evaporated? Only 4. That means what happens? Initially, the vapors produced by the pure solvent will be maximum. But now, after dissolution of the solute particles in that, what happens? What you observe? The number of the solvent particles evaporated will be less. Is it fine? So we can say that, and if you add more and more solute in that, then per unit area, the number of particles which are number of solute particles which are added in that, they will be increased and the solvent particle will decrease. So therefore, the vapors molecule will be less. So everything depends upon the mole fraction of the solute added in that. More is the mole fraction, more is the quantity of the solute particle, less will be the vapor pressure of the solution. So for the increasing of the vapor pressure of the particular solution, we need to increase the solvent molecules rather than the solute molecules. So here, mole fraction of the solution will be depending upon the mole fraction of the liquid number 1. So now when we remove this one, P1 is equal to what again? P1 not the next one. So everything depends upon this part. So solute molecules which decreases the particular area or particular space, is it fine? So that what happens, the solvent molecules will be evaporated, but this will be in the lesser quantity as compared to the pure solvent. Is it fine? If you plot the graph of this one, then what happens? This is the vapor pressure and this is the mole fraction. Is it fine? This is the mole fraction. Is it fine? So if you talk about only the pure solvent, then it will be a straight line. It will be a straight line. I hope you understood this thing. That means vapor pressure of the solution which is made by solid is dissolved in the liquid, then the vapor pressure will be depending upon the quantity of the solute added. Less solute, more vapor pressure, partial pressure we can say, and more solute, less will be the partial pressure. Is it fine? So both are inversely proportional. That means the solvent vapor pressure will be directly proportional to the mole fraction of the x1, that is only in the solvent form. I hope you understood this thing. और solute अगर कम क्वांटिटी है solute की तो vapor pressure ज़्यादा हो जाएगा, और अगर solute की क्वांटिटी कम ज़्यादा है तो vapor pressure कम हो जाएगा. I hope you all understood this thing. The vapor pressure will be taken in terms of the partial pressure, that is P1. Is it fine? Any problem? So solid gas dissolved, and can you give examples of the gas dissolved in the solid? Okay, fine. The topic was taken earlier. Gas dissolved in the, we can say the foam. Foam in the example. This is an heterogeneous solution. It's a colloidal solution in which the solid particles is taken as a solvent and the gas is inserted in that and you can form the foam. And this example has been discussed earlier in the class. Fine. And the next one, rate of evaporation decreases due to the presence of the solute on the surface. Yes. And the rate of condensation remains same. And see. Now just listen. Here the question is rate of evaporation decreases. Okay, rate of evaporation will be decreased. Of course, decreases because the number of particles on the surface of the solvent will be lesser. So the condensation rate will also be decreased because less number of the particles are there. Less number of the particles are there, they will be, less number of particles on the surface will be less, so evaporation will be less. So whatever the number of particles are present in the vapor form, they will only be condensed. So condensation and the evaporation both will be different from that. Because in the vapor form, no solute is present. but in the liquid form, the solute is present. So evaporation depends upon the solute quantity, but the condensation does not depend because it is the purest form. I hope the answer is clear. Now the next thing is that how the graph of vapor pressure and the mole fraction is straight line. See, this is for the solvent molecule. If the solvent, see, if you talk about that, if you decrease the number of particles in the solution, that means the solvent is more. Is it right? The solvent will be more, the mole fraction of the solvent will be more. So vapor pressure of the solvent will also be more than that. It is the straight line, and we have to follow this one because the solid is a non-volatile. It is not producing any kind of the vapor. So therefore, we can say that everything depends upon the vapor pressure of the solution depends only on the solvent. So we'll take the vapor pressure in terms of the partial pressure only in the solution in terms of the solvent, not in the this one solution form. I hope this is clear. Now next thing is that this question was asked, sir, how does the volume remain constant? Beta, just I think you didn't listen this earlier when I started. You see that if we take an example of the water, right? And water is a liquid form, and according to the properties of the solid, the states of the matter, solids are having the very less intermolecular space, right? And the liquid are having the somewhat larger intermolecular spaces. Now, if you take the solute, which is soluble in the particular liquid, so when we try to dissolve, is it fine? Then it will be either dissociated or what happened? It forms a hydrogen bond or something like that. And where these solid molecules go, these solvent molecules will enter in the intermolecular spaces of the solvent. Therefore, no change in the volume. Suppose in a class, we take in another example. Suppose in a class, in your class itself, the capacity of the sitting student is 50, right? And that day, only 40 students have come. How many students? 40 students have come. And the number of benches are saying this decides the volume of the particular solvent. Is it fine? Did you understand? Now, we brought few more students. How many? 50 capacities there. That means the volume of the class is 50. The volume does not change. Is it fine? 50 is the volume, 50 capacity is there, and we have 40 students. Now we brought the 10 students in that. So where these 10 students will go? These students will sit where the empty spaces are there. So what will be the volume now? It will be the 50. The capacity of the 50 was there. Is it fine? Is there any change in the capacity? Answer is no. Is it fine? So that means we can say that intermolecular space present in the solvent in which the solute particles have entered, and they will not increase the volume of the particular solvent. Is it fine? So the solution volume will remain same. I hope the topic is clear. Is it clear? If the density of the solute is more than the solvent, so what? So what? I'm giving one more example. Like if you take water and the density of the salt, common salt and NaCl, the density of the common salt is more than that of the water. Will it not dissolve? Of course, it will dissolve. It will 100% dissolve. Why? And it will be dissociated. It forms the respective ions, sodium ions and the chloride ions, and these ions will get occupied on those spaces where the empty space is present. Is it fine? So we cannot say it does not depend upon density. Is it fine? But it should be soluble or non-soluble. It depends upon the solubility, whether it is soluble or non-soluble. If the density of the insoluble solute is more, then it will sink in the solvent. But the condition is that it should be insoluble. And if the density is less of the solute, is it fine, which is insoluble in the solvent, then it will remain on the surface. Is it fine that you have studied in the physics? Is it fine? But I am talking about clearly, just listen it clearly. The solute particle should be soluble in the solvent. Then only the things are considered. Is it clear? I hope all are clear with this topic. Is it fine? Ashwini Sharma, just listen, beta. One second. The solute molecules still fill up the empty spaces of volume remains constant. Okay, fine. Due to the intermolecular space, volume remains constant. Okay, fine. Okay. Nimbu pani, yes, good example. We can say Nimbu pani. You can do one thing today. You are at home. So you can make a nimbu pani for your parents and even for you. You can take one glass of the water. See that this is the experiment I have given to you, and whenever the school opens, or you can chat me with the WhatsApp. Is it fine? You do one thing, you take a glass of water. This will be taken as a solvent, and you take a lemon juice. Squeeze the lemon. Fine. Okay. Remove that the particles which are there, the flakes are there in the lemon. Okay. Just squeeze that and take this juice and just mix that and add some amount of the sugar in this, and just let me know what will be the volume of the solution. Is it fine? This is the task given to you. So your parents will also be happy that my son has given me the nimbu pani, and even the task will be clear. Is it clear, student? Okay, so this is your task. Okay. Salt plus water solution, absolutely right. Volume will not increase as the solid particles are filling up. All the answers are same, beta. Their languages are different. You can see that all the students are giving the same answer. Is it fine? But the language, the way of writing is different. Is it fine? Okay, sir. It's written. Okay, fine. Thank you. The topic is clear, I think so. Is it clear? So, that's it. Now, the next thing is coming. That was a solution which we made by dissolving the solid in the liquid. Now, come to the next topic. What type of the solutions can be there? Fine. So, very simple thing and very common thing which we take. We talk about the two types of the solution. The one is your ideal solution, and the second will be your non-ideal solution. Okay, this is the next topic. Can anyone knows that if I take, see generally what happens, if I take 1 liter of the liquid 1 and 1 liter of the liquid 2, when we mix them together, yeah, students, though 3 students are sitting in front of me, I am just asking the question to these students, they will also give the answer. Okay, so what is that? 1 liter of the liquid number 1 and 1 liter of the liquid number 2, if we take them together, we mix them together, then what will be the volume? Everyone knows that. 2 liters, you say that 2 liters. Is it fine? Okay, obviously this is the correct thing. Is it fine? Many of the students say that. Okay, we take 1 liter of the liquid number 1 and 1 liter of the liquid number 2. When we mix them together, what is the answer? You will all say that it will be 2 liter. Of course, I understand this part. Yes, this is true. It will be 2 liter. But if I say many of the liquids are there, if we mix them together, is it fine? Like you can say that toluene and benzene. If you take 1 liter of the toluene and 1 liter of the benzene, is it fine? When we mix them together, and the expected answer should be 2 liter. Fine, but it's not. It's absolutely wrong. It will form only 1 liter. Are you getting me? So let's see that how it happens. This is container 1, in which this is the volume of the liquid that will be taken as 1 liter, and this is the second number that will be 1 liter. And if you take this, then the quantity will be 1 liter. Now, when we mix them together, the volume should be 2 liter. The expected volume should be 2 liter. Is it fine? But few of the liquids in the chemistry, I have given the example. One is this one, toluene and benzene, and hexane and heptane. Okay, 2-3 liquids are there. Okay, which we when we mix them together, the volume 1 plus 1 should be 1, but in those cases the volume remains constant. That will be only 1 liter. That means we can say V final will be equal to V initial. Is it fine? So here we'll talk about the delta mixing of the volume will be equal to what answer? V final minus V initial. According to this one, what is that? V final minus is equal to V initial. So therefore we can say delta mixing of V will be equal to 0. Is it fine? Because initial volume 1 liter, after addition only 1 liter is there. Only 1 liter. Is it fine? No 2 liters, it's 1 liter. And there is no change in the volume. So such type of the solution in which delta V will be equal to 0, there is no change in the initial and the final volume, such solutions are called as ideal solution. Is it fine? And those which make 2 liters or more than 2 liter or less than 2 liter, whatever is there, delta V will not be equal to 0. In that case, those solutions are called as non-ideal solution. So mostly we see in the day-to-day life, these are the non-ideal solutions. But in the chemistry, there are few liquids which we mix them together, we get the there is no change in the volume. So this is the first law, your first definition, your first description of the ideal solution. So we can say the ideal solutions are those solutions in which the initial and final volume will be same. Is it fine? Now the second task. You see that whenever you take a solvent and you try to dissolve a solute in the particular solvent, what happens in this case? When we dissolve it, either heat energy is liberated or heat energy is absorbed. So there is a change in the enthalpy of the dissolution. Is it fine? So either enthalpy will be positive or enthalpy will be negative. Enthalpy negative means what? Energy is removed, energy is evolved, and enthalpy positive is energy is given to make the solution. Did you understand? So in case of the ideal solution, what happens? So the same thing is that the enthalpy, we can say that H final, the enthalpy of the dissolution, initial enthalpy, enthalpy, final enthalpy means solution enthalpy. And initial enthalpy, that was when both were not mixed together. So initial enthalpy means there is no mixing of that. Enthalpy final means what? When both are mixed together. If both are same, so we can say that delta mixing H will be equal to what? 0 again. So there is no change in the enthalpy. Neither energy is absorbed nor energy is evaporated. Yeah, evolved. Which energy? Heat energy or any kind of energy. So such type of the solutions are called as ideal solution. Is it fine? So two conditions. One more condition is there. Although two more conditions I'll explain. The first thing is that initial and final volume will be same. Is it fine? Delta V will be equal to 0. This is the ideal solution. If this is not equal to 0, then it will be non-ideal solution. Come to that. Enthalpy of the mixing of the enthalpy of the solution, it will also be 0. Is it fine? Initially and finally it will be equal. So enthalpy of the solution will be 0. There is no change in the enthalpy after dissolution. In that case, we can say this is also the ideal solution. If there is a change in the enthalpy, that means either heat energy is absorbed or evolved. In that condition, we can say that solution is non-ideal solution. Is it fine? And the third rule, those solutions which follow the Raoult's law. What was the Raoult's law? P1 is equal to P1 not x1 and P2 is equal to what? P2 not x2. So those which follow the Raoult's law, these are called as ideal solution, and those which do not follow the Raoult's law, that means P1 is not equal to P1 x1 and P2 is not equal to P2 x2, these solutions are called as non-ideal solution. I hope you understood this thing. So 3 points we have discussed. Now the fourth point is there. You know that if you talk about the liquid number 1, this is the A type, and this is liquid number 2, this is called as the B, this is the B type. So the interaction present with them, that will be the A type, and the interaction present between the B is B type. Is it fine? Clear? So A means only A type of the molecule, and the interaction will be A type. B type of the solvent, that means the only B type of the molecules are present, interaction will be B type. When we mix them together, now we got the new interaction, that is A type. Is it fine? Then this is the new interaction. What kind of interaction? It can be the hydrogen bond, and it can be any van der Waals forces, any force can be there. That's when interaction we can say. So if the interaction between the A and B will be equal to AA or BB, the such type of the solutions are called as ideal solution, and if the interaction of AB is not equal to AA or BB, such type of the solutions are called as non-ideal solution. So there are 4 conditions. I hope you understand. There is a, you can make a line at the center and you can divide into the 2 parts. One is ideal and the second is a non-ideal. The ideal is what? There is no change in the volume after mixing of the solvent 1 and the liquid 1 and liquid 2. There is no change in the enthalpy. I am talking only ideal solution. They obey the Raoult's law, and 4th thing, interaction will be same. So these are the ideal solution, and which do not follow these laws, is it when they all are called as a non-ideal solution. I hope all of you understood the same. Now any question finally? Not any component, beta. This is Rigveda. You are asking, so if we take any 2 organic compounds, will they form? Not any, beta. I have given certain examples. Not all the liquids are ideal. Few. Say ideality. Obviously, in the nature, ideality is very less. We try to achieve the ideality. Is it fine? But they are not 100%. Even I am saying that the solutions I have already given the example. These are near to the ideal. 100% ideality is not possible, but these are the nearest to the ideal solution. I'm getting so few of the solvent. Is it right? Few of the liquids, sorry, few of the liquids which mix together and they form towards the ideality. Is it fine? Towards the ideal solution. Now, so please explain the third point again. Third point was that those solutions which follow which obey the Raoult's law. Raoult's law is P1 is equal to P1 not x1 and P2 is equal to P2 not x2. Those which obey the Raoult's law are ideal solution, and those which do not obey the Raoult's law are called as a non-ideal solution. This was the third point. And the fourth point was there, this is based on the interaction. This is an interaction AA, interaction B. This is a QRS form. Now combine them together, new interaction AB, and I'm saying that AB will not AB interaction will be equal to AA and BB. Is it fine? Such solutions are called ideal, and the interaction between AB is not equal to A or BB. So in that case, this is the non-ideal solution. Now I think all 4 points are clear. Is it clear? So intermolecular force equal of AA and BB, and yes, of course. Shalini Srivastava, it is true. Yeah, for the ideal solution, the thing which you have written, that is for the ideal solution. But non-ideal solution do not follow this thing. Now, this is possible, beta. This is possible. That's why I have given only few examples. Benzene and toluene. Is it fine? Because again it comes on the intermolecular space. Is it fine? So when intermolecular space will be more, so these particles will have the same interaction with that. So they have that much of the gap. So when we will come regular to the school, we will explain everything practically. Is it fine? I will show you this part. Is it clear? So this thing can be clear. Before we read that, when the Raoult's law, the solute is dissolved. Yes, beta, Kavita Agarwal, you have written that before we read that in the Raoult's law that the solute is dissolved in the solvent. Yes, that was when the liquid. These are the certain different examples. Are you getting me? These are the certain different examples. So we try to make them solution ideal. Is it fine? That's why we are following all these things. Hexane and heptane. Don't write this in hexane and heptane. N-hexane and N-heptane. Okay, done. So all doubts are clear. So we'll proceed the next topic, that will be non-ideal solution. Mostly the solutions are non-ideal. So all doubts will be cleared, and new topics will take next time, that will be the azeotrophs, and we'll talk about the graph today. I didn't have much time to explain this thing, so we'll discuss this thing tomorrow when the lecture will be there. Thanks for today. Have a nice day, students.
How
was the